We begin with what I hope is a fairly comprehensive review and possible introduction to the information that you need to know for the upcoming test. As I told you, chemistry is the foundation of biology. Therefore, we need to have at least a basic understanding of chemistry in order to proceed through biology and have every part of biology make sense. Really, truly, chemistry has its basis in physics, and physics is the most fundamental of all sciences. However, this is not going to include a lot of physics at this point. We're going to mostly focus on focus on chemistry. Now, chemistry is going to look at the atom particularly. Chemistry is the interaction primarily of electrons moving between one atom and another. Now, there is also the need for an understanding of protons and neutrons with the atomic number and the atomic mass. But when we're actually talking about chemistry, the most important subatomic particle or the most important component of the atom are the electrons. And we did see, I mentioned previously, the Bohr model comes from Niels Bohr, who really helped us work out an understanding of the atom in this sort of a format. Of course, this is a very simplified model of what an atom actually looks like, because we just don't have the capability of truly conceptualizing an atom as it actually exists. But this is a very close approximation, which gives us an idea of what we need to understand about the atom. If we look at the nucleus, what we need to know is that the atomic number equals the number of protons. Therefore, something like carbon with the atomic number 6 has 6 protons. Hydrogen has 1. Oxygen has 8. Sulfur has 16, and we go on from there. Phosphorus has 15, potassium has 19. I'm just pulling these out of my memory, so I hope they're all correct. Therefore, as I said, carbon's number 6, sulfur is number 16. Protons have the positive charge. Now they will need to be balanced by electrons in a neutral atom, because a neutral atom has an overall charge of 0, and neutrons do not contribute any charge, so the number of protons must equal the number of electrons. However, because electrons are so small, they do not factor into the atomic mass. You'll see here that atomic mass is the number of protons plus the number of neutrons. And an example there would be carbon 12, with 6 protons, 6 neutrons, 6 plus 6 equals 12. Carbon 14 has 6 protons and 8 neutrons, 6 plus 8 equals 14. If it had 7 protons, 7 neutrons, now you're talking about nitrogen, not carbon anymore. And the other important thing that you need to understand here is that I didn't make these letters correct, but I'll have to improve that on a later version of this video. Electrons are the basis for chemistry. Electrons have a negative charge. They do have a mass, which is actually kind of surprising. We hadn't originally expected them to have a mass, but they do. And that mass is well known, but that mass is very tiny compared to the remainder of the atom. Electrons can only be found at specific energy levels away from the nucleus of the atom. Now, electrons are negatively charged. Protons are positively charged. Therefore, electrons should want to go into the nucleus to find the protons. However, they can't, because these specific energy levels where electrons exist are not intersecting with the nucleus at any point. Electrons at the outermost energy level will determine how an atom behaves chemically, meaning what will it react with. We'll hopefully see some examples. What kinds of bonds does it make? Does it make ionic bonds? Does it make covalent bonds? Does it make polar covalent bonds? All of that is based on the outermost energy level electrons. Then we need to know the rules for those orbitals in the Bohr model. The first orbital, that first inner ring, can hold up to 2 electrons. The next orbital and the one up above that can hold up to 8 electrons. I'm sorry, my writing there made me get confused about a little bit. Okay, so let me get rid of that and we'll go back to where I was. The next orbital can hold up to 8 electrons. Those 8 electrons occupy 4 specific regions of space. Now, the actual shapes, we're talking about one thing called an s orbital and 3 p orbitals. You don't have to worry about those shapes until you get to chemistry next year. Each region will get 1 electron, and then once each of those 4 regions get 1 electron, then they start to pair up, as we will hopefully see a little bit later on. Again, my numbers are all messed up. The next orbital, which is the 3rd energy level, does hold 18 electrons. However, it will fill up with 8 first. And what happens is we have another orbital in there, what makes it all the more confusing. But what you really need to worry about, we're only going to primarily deal with atoms at the first 2 energy levels. So hydrogen, for example, 1 electron at the first energy level. Carbon, 2 electrons at the first energy level. And then, since it has 6 electrons, because it has 6 protons, 4 of them at the next energy level. They are each occupying different regions of space, and since they are all unpaired, they can each form a chemical bond. Carbon's great at forming multiple chemical bonds. Nitrogen, each of those 4 regions of space got an electron. Then, since it actually has 5 outermost electrons, 2 on the inside, because its atomic number is 7, these 2 pair up. These 2 are not available for bonding. When we move on to oxygen, these are not available for bonding, and these are not available for bonding. However, this one is, and this one is. Therefore, nitrogen can make 1, 2, 3 bonds. Oxygen can make a maximum of 2 bonds. What atoms will do, according to this octet rule, is they want to have 8 electrons at their outermost layer. Except hydrogen would want to have 2, or hydrogen, as we'll see with acids and bases, hydrogen can lose this electron, be 1 naked proton, and is actually fairly happy in that condition as well. Metals will lose electrons because in order to get to this number, magic number 8 or magic number 2 at the innermost level, the best way, for example, sodium, which has 1, 2, 3, 4, 5, 6, 7, 8 here, and then 1 on the outside, sodium will lose that outermost electron, and then it has the 1, 2, 3, 4, 5, 6, 7, 8. Now, I realize that's not the atom of sodium, but you can use that as the model for what sodium would do. Here we have, as I've explained, the periodic table. What you need to worry yourself about are that everything on this side of the staircase is a metal. Therefore, sodium's a metal, magnesium's a metal, potassium, calcium, chromium, manganese, iron, cobalt, nickel, silver, gold, platinum, osmium, iridium. All of these, cesium, are all metals. As metals, as elements in general go from left to right, they tend to be less electronegative and then become more electronegative. These are what we call the halogens, generally the most electronegative. Noble gases do not want to grab electrons, do not want to give electrons. They really don't factor into electronegativity, but everything else here does. Non-metals tend to be more electronegative. They want to have electrons. They want to grab electrons. Fluorine is number 1. Fluorine is the most electronegative element. Oxygen is the second most electronegative. Nitrogen is the third. These are the 3 that are going to be very good at pulling electrons off of other atoms, especially the metals. In the area here, we see some things that we would call metalloids. So silicon is the most important metalloid. It can act like a metal and just conduct electricity in one state. It can act like a non-metal and not conduct electricity in another state. This is why silicon is so important. It's your 0 and 1 on and off in a computer chip or a transistor is thanks to silicon. Germanium also makes a great transistor. Arsenic, kind of a nasty substance. Antimony, not particularly fun to be around either. However, we're not going to focus so much on the metalloids. I want you to know metals, which will form ions. They will get a positive charge. And nonmetals, which will be ions with a negative charge. The atoms with a positive charge, we call them cations, positively charged ions. The atoms with a negative charge, we call them anions, and they are generally nonmetals, especially the halogens, will form very good anions. Oxygen will as well, so will sodium. Nitrogen will. Phosphorus some, but again, phosphorus is not very electronegative compared to nitrogen, oxygen, or fluorine. Same thing with sulfur, not nearly as electronegative as the big three up here. So generally, you'll see sulfur in a nonpolar sort of a compound. Chlorine, relatively nonpolar. Phosphorus, fairly nonpolar. Bromine, a lot less polar, but fluorine's number 1, oxygen's number 2, nitrogen's number 3. They all form very polar compounds because they're very electronegative, which means they want to grab electrons. For biology, we need to know our carbon, hydrogen, oxygen, nitrogen, as well as phosphorus and sulfur. When we've talked about macromolecules, carbohydrates, carbon, hydrogen, oxygen. Lipids, carbon, hydrogen, oxygen, except for the phospholipid, which has a long carbon and hydrogen chain and then a phosphate group on the end. The amino acids, carbon, hydrogen, oxygen, nitrogen, occasionally sulfur in some of these amino acids. And then the nucleic acid is carbon, hydrogen, oxygen, nitrogen, phosphorus. That's how you can tell, at least get a basic starting idea of what sort of a monomer you're looking at in these particular cases. Here we just see a little bit of information about some sugars, ribose, glucose. We see some of the lipids with those long carbon hydrogen chains. And then we have the amino acid. All of these, you may remember, are pulled together with hydrolysis, which was another video that we covered. Looking at the atoms and where their electrons are, we can see that hydrogen has 1 electron, helium has 2. That's the maximum number of electrons at that energy level. Lithium has 3. Now, lithium would prefer to look like helium, so lithium will generally lose this electron, have a +1 charge because it has 3 protons and 2 electrons, and it will give that electron to something like fluorine or potentially oxygen. Fluorine only needs 1 more electron. When it gets 1 electron, it will have 1, 2, 3, 4, 5, 6, 7, 8. It will have its octet. It will be happy. It'll look like neon. But since it only has 9 protons and 10 electrons, it'll have a -1 charge. Chlorine will do exactly the same thing. Chlorine gains an electron, it'll look like argon. Where does chlorine get its electron from? Something like sodium with 1 electron on the outside. The electron goes here. This is a -1 charge for chlorine. This is a +1 charge for sodium, sodium chloride. In that case, sodium without that extra electron has 1, 2, 3, 4, 5, 6, 7, 8 electrons at the outermost level. Looks like neon. And chlorine gains 1 to look like argon. What we call this is noble gas configuration. Sulfur, you'll notice, has 2 places to gather electrons. It will usually form a -2 anion. So will oxygen. Nitrogen will form a -3 because it can gain 3 electrons if it's interacting with a metal. So aluminum nitride, aluminum would give away its 3 extra electrons on the outside. When it gives those 3 away, it only has 8 on the inside, looks like neon. It could give them to nitrogen, which would gain 1, 2, 3, have a -3 charge because of the 3 extra electrons. 10 electrons, 7 protons means an overall -3 charge. And it would also look like neon. That we'll talk a little bit more when we get to ionic bonding. At the same time, if nitrogen, oxygen, fluorine bond with something with higher electronegativity, like hydrogen, they will share that electron. So nitrogen can form 1 bond with 1 hydrogen, 1 bond with another hydrogen, 1 bond with another hydrogen. Oxygen could do 2 bonds with 2 different hydrogens. That's why you have an H2O and an NH3. Fluorine would do 1 bond with 1 other hydrogen. That would be HF. These are the basic dot structures, the same thing we saw here, just with the letters. So fluorine at its outermost energy level has 7 electrons, oxygen has 6, nitrogen has 5, neon has 8. Neon's happy. Neon does not make any chemical compounds. Now, Noble gases have their valence orbitals filled, as I just mentioned earlier, which means they're not interested in making any sort of a chemical bond. They have their octet, they have their 8, they are happy. If we take a metal and put it with a non-metal, you're going to have electrons moving from one atom to another. That will form ions. Something will have a positive charge because it has fewer electrons than protons. Something will have more electrons than protons. That's the non-metal, and that will have a negative charge. So we'll get charged atoms in that case. The charges have to balance. So if I look at my magnesium, has 2 electrons on the outside, 2 electrons ready to give away. If it gives 1 electron to chlorine, it still has 1 electron there. We'll have to find another chlorine to give another electron, which is why we have MgCl2. Mg gave away 2 electrons to be happy. Each chlorine takes 1 of them. So we have magnesium chloride with this. Each of these has a -1 charge. I have 2 of them, and this has a +2 charge. In this case, +1, -1. Everything's happy. If I had magnesium with 2 electrons on the outside and it came in contact with oxygen, which has room for 2 electrons, then oxygen has a -2 charge, magnesium has a +2 charge, it would also be a happy compound. The other thing about covalent bonds, you can have a non-polar, which in biology we're primarily talking about carbon-hydrogen bonds, or you can have a polar bond, which we're generally dealing with nitrogen to hydrogen or oxygen to hydrogen. Those are our polar covalent bonds. These are the basic rules. Once you see this, once you understand this, you should be much more comfortable in looking at various macromolecules and telling me, are they non-polar, polar, are they hydrophobic, hydrophilic? Because if something has a lot of carbon-hydrogen bonds, it's non-polar, it's hydrophobic. If it has a lot of these, or even any of these, it's going to have a polar part, and it's going to be more hydrophilic because water likes to mix with things that have partial charges on them. These are a little bit of more of an overview of how you could look at covalent bonds. So non-polar covalent bonds, they give and take their electrons equally. They equally share them. In this case, we have 2 oxygens. One oxygen can't pull any harder on the electrons than another because they're both oxygen. So what does oxygen do? It shares them completely equally. This is a very non-polar bond. Water, different case. Oxygen pulls a lot harder on those electrons because it's very electronegative. The hydrogens have a partly plus charge and the oxygen have a partly minus charge because those extra electrons stay closer to the oxygen and farther away from the hydrogens. If you want to see, I don't know if these analogies help, but you have a good, healthy relationship where things are given and taken equally. Here you have more of a controlling relationship, although this oxygen is having a relationship with 2 hydrogens. If this works for you, sure, use it. And if we look at something like sodium chloride, what sodium's doing is giving an electron away to chlorine. This is the thing that I've explained before. Don't worry about metallic bonds yet, but they are just positive charges with electrons floating around, and that's how metals can conduct electricity. And then these are van der Waals forces. You don't really need to worry about that, or the misspellings in this. We don't have to worry about those 2 on this table. So just to make sure we understand, what would be the electron? A letter with one electron on the outside would be the electron dot formation for which of these? It would actually be either sodium with 1 electron on the very outside, or the element right below it on the periodic table, potassium, also has 1 electron on the outside. They're both in group 1, which means they have 1 electron on their outside. Sodium looks like neon because of that when it loses that 1 electron. Potassium will look like argon when it loses that 1 electron. Aluminum has 3 electrons on the outside. This looks more like a non-metal. It has more electrons than it's missing. Boron only has 5 electrons total. 1, 2, 3, 4, 5. Can't be boron because there would be 2 on the inside, 5 on the outside. Can't be boron. could possibly be nitrogen, and then right below nitrogen on the periodic table is phosphorus. So either one of those would be the possibility. Hadn't expected there to be an explosion here. Covalent bonds are formed by sharing electrons. As I said, we have the nonpolar covalent bond, which is between nonmetals with similar electron negativities. They share electron pairs. They could be the same element. Oxygen shares 2 pairs of electrons perfectly evenly because each of those oxygen atoms has the same pull on the electrons. Nitrogen shares 3 pairs of electrons, but one nitrogen cannot pull on them more than the other. Methane, carbon, and hydrogen share their electrons fairly evenly because they have similar electron negativities. And then things with longer carbon and hydrogen chains also are generally nonpolar, which means no charges on them because they share their electrons evenly. An example would be fluorine. One fluorine cannot pull on this better than another. They share these electrons. There's no greater charge on one side or the other. They're sharing these electrons evenly. And my fluorine molecule, therefore, is a nonpolar molecule. Polar covalent is when we have nonmetals, usually nitrogen or an oxygen or a fluorine with different electronegativity, something then with a hydrogen. They're formed by sharing electron pairs, but the more electronegative element, looking for nitrogen, looking for oxygen, will pull harder on the electrons. That gives us those partial charges. You've seen this thing before, the Greek letter delta, with a minus or with a plus. The nitrogen or oxygen are partially negative. The hydrogen is partially positive. We've seen that here. Oxygen pulls harder on the electrons. These hydrogens are still connected to the molecule. They're still sharing the electrons, but those electrons get pulled farther here, which gives us a partly negative charge on the oxygen and partly positive charges on the hydrogens. This is a polar molecule because this is pretty much a permanent negative, slightly negative charge. This is a permanent, slightly positive charge. That makes the water sticky. That's what causes hydrogen bonding, which is an important thing to deal with because this hydrogen with a slightly positive charge is attracted to an oxygen on a different molecule with that slightly negative charge. And this is why water molecules will stick to each other. We saw in the Water Olympics how much water likes to do that. Something I haven't gotten into tremendously are when we share more than one pair of electrons. If we share 2 pairs of electrons, we do have what is called a double bond. Now, this is a different geometry in the molecule. If I have a fat, a lipid with carbon and hydrogen bonds, single bonds, single bonds, single bonds, at this point it's going to twist. And it's going to change the shape of the overall molecule. And this means that one lipid with this twist doesn't stick as well to another lipid with the same twist or a different twist. So what happens is these things with the double bonds, these lipids tend to be liquids at room temperature, whereas the ones with carbons, all single bonded, they tend to be solids because they can line up nicely next to each other. What we don't see a lot in biology are triple bonds. They are possible in some organic molecules, but what happens in a triple bond is that 1, 2, 3 pairs of electrons, 6 electrons are shared between, for this case, carbons or nitrogens. The only atoms that really make good triple bonds are carbon and nitrogen. There's no such thing as a quadruple bond, but there are triple bonds, particularly in nitrogen and carbon. Now, just to review ionic bonds, we have to have atoms that are metal and nonmetal, where an electron is moving from one atom to another. They produce charged ions, meaning one atom will be a cation with a plus charge. One atom will be an anion with a minus charge. The cation has more protons, less electrons. The anion has more electrons, less protons. That's why the anion is negative and the cation is positive. In most cases, ionic bonds will conduct as liquids because they will have charges, and they also have a high melting point because they do stick together very nicely. Sodium chloride, calcium chloride, potassium oxide are examples of ionic compounds which have ionic bonds within them. There you can see a nice example of sodium giving away its electron, that outermost electron, giving it to chlorine. Chlorine gets a minus charge. Sodium has a plus charge. And because you have a plus and a minus, they stick together very nicely. This is what the actual reaction would be. Would release a lot of heat. It would be a fairly exothermic heat-releasing reaction. And this, I don't think the video is showing, but what you would see here is, not that, but you would see these. If water came in, water has, this is a positive charge, this is a negative charge, positive, negative. Water would see this. A negative part of the oxygen would pull this out into the solution. Positive connections to the hydrogen would pull this out. And that's why this whole crystal would dissolve in water, because the water molecules have charges on them. So do the sodium ions, and therefore the water molecules will carry away these charged particles out of the crystal and break the crystal apart. Here we see another example again of sodium and chlorine. Sodium transfers its outermost electron to chlorine. Therefore, at the next level down, 1, 2, 3, 4, 5, 6, 7, 8, sodium's happy. Looks like neon. Chlorine originally wasn't happy, but now it gains 1, 2, 3, 4, 5, 6, 7, 8. Perfectly happy, looks like argon. This is why atoms make these interactions in order to get to something like a noble gas configuration. And with that, we're concluding the slideshow. I hope this was a good review.